Good evening, everybody. My name is Yelena. I'm one of the teaching assistants in the data analytics program. So today we're going to discuss the clustering method, and this session will be recorded. All right. So let's go ahead, get started. This is an agenda for tonight, and we're going to talk about the data preparation for k-means clustering. I'll show you how to run the method, how to look at the results, and we're going to look at cluster-to-class comparison, cluster plots, and then we'll discuss the elbow method to estimate the optimal k-value, and then there is a bonus, right? So let's go ahead. This is what we're going to do. This is a data set that we'll look at. This is a source. And the data contains information on the chemical compound of the glass samples. And our task is to find similar glass samples and to combine them. Right? So based on the chemical compound, we're going to identify the groups of similar glass samples. Right? And, well, I understand that each glass sample is labeled with a glass type, but we are going to omit the label. We are going to pretend that there is no label on a sample, right? And we have to look at the chemical compound just to determine which samples are similar and place them in the same group. And let's say the optimal number of groups in the unknown, it's our task to determine. Quick review, the difference between clustering and classification. Clustering is an unsupervised learning, which means that each observation, in this case each glass sample, it does not have a label. We are not going to build a classification model. We are not predicting a class. Then there is no dependent variable. Remember that, right? So when we do classification, we know the number of classes in advance, right? Here we don't. We don't know the optimal number of k. Our task is to estimate what it is, right? We're not going to split data into training and test sets, and we're going to utilize all variables, almost all, and I'll explain why. And there are no weights. No weights are assigned to variables, right? Remember when we used some other methods, some classification methods, the variables were assigned to weights. It's not going to be the case in here, right? Because this is a clustering. We don't have a label, right? So now I'm going to start sharing my screen, and we'll talk about the data pre-processing. But in summary, the glass data set, it has the unique identifier. This is what we want to remove because we don't want it to have an influence on how we determine the sample membership, right? The cluster membership, rather. Then we're also going to remove the class label because we don't want it to have an impact, right? We don't want the class label to have an impact on results. And of course, we're going to scale the data. And the reason is that we want all variables to be on the same scale. So if the actual variable has a larger scale, we don't want this to have an impact on outcome, right? So let me go ahead and share my screen. I'm gonna go straight into the RStudio. So I wrote the script for you, and I'm going to share this script with you after this session. Now, cluster package is actually pre-installed. I'm looking at the latest R version, which is 3.44. Right? This is the version I have installed right now. 3.4.4. In this version, the cluster package is already pre-installed, and you need this package for visualization. Okay? You don't need this package to run the message, but you're gonna need it for visualization. And it's one of the it's one of the system library, right? It's pre-installed. So, but for package to be available, I have to run the library command. It could be, there are two ways. You can do library or you can do require. Okay? Next, what I have to do is I need to set my working directory, because on my external hard drive I have a folder and I called it datasets, and that's where the glass file is saved. And it's a CSV file, and I want to read the first row of my header, so I want to read it as a header. So that's the reason I set it T. Okay? So now what we're gonna do is, this is a class data set that I've read, right? It has 11 variables and there are 214 samples. The view command, you always want to run a view command just to preview the data. Well, not always, but if the data set is relatively small, you can do that. But if the data set was large, I would have to look at, perhaps, I would have to use the head command to look at the first 6 records. Something to point out here, one of the variable names is called NA. Since NA stands for the missing value, right? R renamed it for me. Do you see this? NA dot. So that's how R renamed this for me, because the name was NA. Another thing to point out is that the first variable name is ID. So when you take the Microsoft, when you try to open a file, the CSV file in Microsoft Excel, you might be getting some warnings. You might be getting some messages. It's because the first variable name is ID. Microsoft Excel could give some problems, right? Okay, so here's my class type, right? We are going to remove the ID and we're going to remove type. But later on in the analysis, I'm gonna need my type, right? I'm gonna need that for the later part of the analysis. So instead, I'm going to create a new data frame as a copy with these 2 fields removed, right? So let's see what I'm doing here. Well, first of all, I want to also do the summary command. And the reason is this method that we're going to use, all our variables, they have to be numeric. We cannot have categorical variables. I want to make sure that I'm okay. It looks like we're fine, right? Now, looks like we don't have missing data in this data set. We don't have missing values. All right. So now I want to look at this. I want to look at my class distribution, right? Class label distribution. This is just for me. Do you see this? It's a little bit unbalanced. So in theory, if it was a classification problem, I would probably combine these guys, more likely, right, into the same category. But for right now, we are going to pretend that there is no label. I'm going to peel the label off, right, the sample. So to do that, I'm creating the new class, right, and I'm going to assign it a class. I first copied. Now I have to remove the ID, and one way to remove it is just set it to null. And I'm working this as a copy, right? And now I'm going to remove the type. Now, for the scale, there is more than one way to do it, but what I'm doing here, I loop through all the variables, right? See this names, this piece here, it returns the names of my fields, right? Here. So I'm looping through all of them, and I'm scanning them, right? That's what I'm doing here. Okay, so let's actually run this code. Oops, I went too far. But let me show you what I did here. We want our results to be reproducible, right? In order for results to be reproducible, we have to set the seed value. Because when we run the method, our initial cluster assignment is random, right? So we want, every time when we run the method, we want it to assign the initial cluster center the same way. Because if I did not do that, and I'm writing my report for gradient, and I would have next day, I cannot continue from where I left off. I would have to restart, right? And I would have to redo all the write-up, because my screenshot would be different. Alright, so then I'm gonna do this. I usually like to pick 1, 2, 3, 4, but it's a matter of choice. Now I'm ready to run the method, and what I did was in the slide I summarized everything for you, what I'm doing. Like here I did the data pre-processing, and here this is how you run the method. So you have 2 input parameters. The dataset name is required and key value is required. Here you could also specify the maximum number of iterations. So this is what happens. The method takes random points, right? to make them as a cluster center. On each iteration, every instance, right, every glass sample will be assigned to the closest cluster center. And after that, the new centers will be recomputed, right? And the glass samples will be reassigned. And the process continues until there are no more assignment changes. Or we can specify where to stop, right? But this is optional. So what I'm going to do is, I'm first going to start K6. I'm going to start with 6. And let's run this. So here, this is the data, and this is a K value, right? So let me run this. Okay, so what I did was I stored my output in a variable KC. I can just go ahead and type KC, right? But the problem with that is that I don't see all outputs that I want to see. And in this case, we have a small data set, we're fine. But if the data set had 1,000 records, here you would have 1,000, right? Because see this clustering vector, it shows the cluster membership for every glass sample. In our case, it's a glass sample, right? So here, what it's telling me, it tells that I have 6 groups of glass samples, and this is the number of samples in each group, right? And remember that this, right, does not match, it may or may not match what we did up here. See this, we checked the glass type. This here may or may not match what you see here. The numbers are different, okay? Here are my cluster centers. So basically, this thing here, so I have 6 clusters. This is a center, right? So let's say we have a glass sample, and this is the composition of the glass sample at the center. You can think of it this way. So this is a chemical compound of the glass sample located in the center of a cluster, right? And we're checking the distances to determine where each of the 214 samples belong. Right now, I have 6 clusters, right? Now we're going to look at other things here. So this is the centers. I have the membership. This is a sum of squared by cluster, right? But what is it? Let me show you what it is actually, to make sure that you fully understand. This is the Euclidean distance. So just imagine, I have this picture here. Just imagine point A is a center and point B is the glass sample, right? Let's look at it how it is in 2 dimensions. Just imagine you have two dimensions, 2 variable only. This is the center, right? This is the sample. How do we get the distance? Do you see this? We have to drop the line from point B perpendicular to the x-axis and line perpendicular to y-axis. Then we take in the center and we take the line perpendicular to x-axis, perpendicular to y-axis. So this is the right triangle, right? So we have this leg, and hypotenuse, right? So remember the theorem from back from math class? So this thing squared is equal to each of this squared, right? So the length of this blue piece is x2 minus x1, and we take it squared. Then we do plus, and we take the difference, right? y2 minus y1, and this is squared. And this is this distance squared. So that's what it actually is. It works the same way when you have more than one dimension. It would be something like z2 minus z1 and also squared, right? That would be sum. So this is how it works for every single glass sample, and then we add them up. We calculate this distance for every single glass sample in a cluster, and then we take the sum. This is what it's actually doing in here, but I decided to put this picture for you. It might help. Okay, so let's go back here. So this is what it's doing, and it's gonna show this for all of them, right? And then it also it's not displayed in here, but I'll show you how to get it. We can also take the sum, right? We're looking at the sum of this. Then what we also do is we look at the sum of squares between clusters. So basically, see, this is a cluster center A, and this is a point B. Maybe there is C somewhere in there. So here, since B is not in the same cluster where center C is, we would take a distance between A and C, right? So for each of these points in cluster with the center A, we take the distances to other centers, to other non-membership clusters, right? So there are 5 more centers. We have to look at the distance between this point and 5 other centers, right? And we do it for all points. So this is what it's doing in here. See this? And then, so we take these guys right here, this sum, plus the sum of squared with non-membership clusters. And this is total SS, right? So here, this is the distance between, right? And this is a total. And this is how they got this number. Okay? Now, what I want you to notice that the output from k-means clustering, this is actually a list, and I'll show you, because it has this component. See this? This is a list, and it has these components. So we run. Suppose that we don't know what the output components are. Remember that we can run names command. Names command, we ran it to get the variable names, but we also can get it names of the elements of a list, right? So that's what it is. This is how you access the individual sections of the output. See this? KC, and then you put the $sign and put a cluster, right? So this will give us, this is a cluster membership. Here, supposed to give us the centers, and this is the total sum of squared. But here, this part in here is within. So that's gonna be for every single cluster. We calculate the distances, square distances between each point, right? Each class sample and a cluster center, and we add them up. And here is a total of these numbers, right? This is a total of these 6 numbers. And between, it's between clusters, right? So these 2 guys right here should approximately add up to that guy. If you scroll up, you'll see it. It's a little bit rounded, but approximately that's the sum, right, of total distances. One thing to note is that no matter what k value you use, this number will be the same. This number will be the same, just notice that. Now, this piece right here, size, it's going to tell you how many samples we placed in each group. This one will tell you how many iterations did it take to run the method. In this case, it's 3. And this one, it returns 0 if the method ran as expected, right? So this is something for you to know. And what I did was I put it here. I summarized what we did. In your homework assignment, you want to look at these pieces, right? And you want to explain what they mean, right? So I kind of put a summary for you, right? And now we're going to look how the clusters capture each class. What I'm doing here, and I'm going to build a table, and I'm taking glass type that's from here. See this? When I read data from my data set, right? I kept it. I kept the glass type. So let's see how my glass types match the actual cluster membership. So that's here. We're gonna do the cross tabulation. See this table? And then what I also did was I put this. It will add the labels to the output. That's why it's easier to understand. Let me do this. Run. There we go. Take a look at this. So we have 6 clusters, right? You might be wondering what happened to. Oh wait, cluster number. Okay, take a look at this. There is no number 4. You might be asking what happened to 4. Well, it's a class label. There is no 4 in this data set. And if you read the description, that's what they say. There is no 4. Now take a look at what's going on. Glass type 1. See this? It's kind of split among the clusters 1, 2, and 6, right? See this? It's kind of like it's not in it did not fall in the same cluster, so to speak, right? If you look at this one, right? This glass type is also kind of split. All of them are, right? Besides type 7, right? See this? Type 7, most of the samples are in the 5th cluster. But in general, you see a lot of overlap. It's not that good, right? Oh, well, we're gonna try different k values, but for right now, this is what you also can do is you can plot the cluster plot, or this is what you can do. I'm just gonna give you this idea. We can take 2 variables. And we can plot the values, and we can plot the cluster centers just to see the distribution. And if you look at it for each pair of variables, we're not gonna do that, but this is for you. If you look at it, it could give you some ideas of how many clusters are there. Okay, well, we're not up to elbow method yet, but I'm just showing different techniques you can do. So here it is. See this? I'm going to plot, and I'm using different colors. And now I'm gonna put the cluster center. See, this gives you an idea. See this? One of the centers is blue, so this is like more isolated. But most of them are overlapping. Do you see this overlap here? I have one center here, one center here, one here. So 1, 2, 3, 4, and there are 2 of them overlap. And if you look at the points, see how they split here? Do you see that? I have a class. See this first class and the second class. These 2 classes are kind of split between 2 or 3 clusters. See this? So that's why I see this overlapping here. But that gives you an idea. Some of you might think, well, looks like 3 clusters maybe is optimal. 1, 2, 1, 2, 3, or maybe 4, right? We don't know. We'll find out. So what we could do is we could try different k values, and this is what you were asked to do on a homework assignment, right? But I'll just show you what you can do here. But before we do that, did I skip this? Yeah, I skipped this by accident, so let's do this cluster plot here. Now, this is one thing that I noticed in this R version. See this labels equal to? Keep it as is. It will label each point with a sample number, but if you change it to label equals 1, I'm not sure why, but the method took forever to run. It's an issue in this R version. I just noticed it. So just keep it 2. For some reason, if I put it a 1, well, option 1 should just draw the points, but it should not label them. But for some unknown reason, there is a little bug in version 3.4.4. So if you put 1 and if you run into an issue, just remember it. I ran into it also. So let's do it this way. Okay, now take a look at this. See this overlap? If I was, just by looking at it, right, I see 1, 2, 3, see this? 4. Well, I would think there are 4 or 3, right? But I need to tell you that the results are different if you don't scale the data, and if you scale the data, you don't get the same results, honestly. So now let's try k equals 3, right? I'm going to try that, and now I'm going to do the cross tabulate again, and take a look at this. I'm having a problem, right? See this? It's kind of split into 3, but take a look again. Class number 7 falls into the first cluster. I'm good here, relatively good here. Here, about half of it is cluster 1, but it's kind of like, I don't like it. It's not the way that I would have liked it, right? We can do the cluster plot and see what happens. Okay, see this? There's also still an overlap. Well, sometimes it's a matter of the data set, but let's try 4. And actually what I should also be doing is that I should be looking at the output. I should be comparing my distances, see this? Okay, I should be looking and comparing. Now let's try the 4. Run. Table. Do you see what happens? Now I'm having a problem too, because it's kind of split. See, there is a lot of overlap between class 1, class 2 are kind of like split among the clusters. Yeah, but see, that's the thing. That's what I did. I scaled the data, right? The plus side of scaling is that you don't want one variable to have a bigger influence than the others. But the minus side is that you lose in the original distribution, right? So if you run it on the unscaled, you'll see the different results. Now what I'm going to do is, so what is the best k value? Who knows, right? I wrote a little code here and I'll let you have it. I'm going to calculate the sum of square distances between the clusters, right? So basically, when the value of k gets larger, I expect the sum between clusters to go larger, and the sum of square distances within cluster goes smaller, right? So our goal is to make the sum of square distances between clusters smaller, larger rather, right? Larger, but within clusters smaller. However, how large is it going to be? When do we have to stop, right? We certainly don't want our k to be the number of instances in data set. That's not what I want to do. On the other hand, we don't want k to be 1, right? So this is what I'm going to do. I'm going to calculate the distances here in between centers. See this? I'm running. See, this is my loop. I'm going from 2 to 15. I'm running the method and I'm taking the betweenness part of it. And I'm going to plot this. Okay? And then I'm going to do the same thing for withinness. So let's run this piece of code here. And this is my loop. I'm looping through this. Okay. 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 So this plot right here is going to be within, right? And this plot here is going to be between. It's increasing. But when you look at this plot, usually the inflection point on the plot is probably the optimal k value, which is what? It looks like it's 2 in this case. In this case, it's 2, right? Or 3, maybe 3, okay? So, but the result that you get is going to be different depending on if you scale the data or not. So now we're running it with scaled. Later, we can try running it with not scaled, see what happens. But this is a surprise part that you may not have expected to see today. There is a different clustering method implementation. And to run this, you would need to install this package, FPC. This package is called FPC. You're going to install it just once, and you have to run the library command to use this package. The difference is there is a function called PAMK. It's also a clustering function, but the difference is that you don't specify the k value. This method will try to estimate the k value for us. However, there is an optional parameter, k values range. For instance, I can say that I want to pick the best k value between 5 and 10, something like that. I can do that. But this method will estimate the optimal k value for me. Okay, so let's just go ahead and run it, and I'm storing the output in a variable called best, right? So see, that's a bonus part of today, because that's good to see more than one implementation. So this is a best, right? And now we're going to look at this output. This piece here, NC, this will show the suggested number of clusters, and it's going to be 2. I just know it. This method suggests the 2. Now, how are we going to get to this? Let me show you something. If you run the names command, names best, it will show you, it will show you the components of the output, right? It's list. Best is a list, and it has 3 pieces, right? We're going to look at this one. So this is a recommended number of clusters, and this one. This is the actual output, right? So now what I'm going to do is, look, there is more than one way to access different components of this. See this, if I do this here, right? Because what is this? If you take a look at this, actually it's in here too. See this? This is a list of 3, and this object contains 10 sub-objects. That's another list. See this? This is another list. So I'm looking at the clustering info component of this piece right here. And the clustering info is going to give us this. There are 2 clusters. Sorry, it's giving you the number of glass samples in each cluster. Right? So it's in here. It's also giving me the distances. So it's taking the distance between, see this, do you remember that slide over here? So we're taking the square distance between each point and cluster center. It's going to give you the average distance and the minimum and the maximum, right? That's what it's doing here. Right. So now this is another way to access this component, right? You can do the $sign. There are 2 ways. It's going to return the same thing. I'm just showing you. Okay. Now this one. This is another piece, and this shows the cluster membership for each glass sample. And here, this is called midoid. It's going to show me the cluster centers. It will show me the cluster centers. Okay, here it is. Now what I'm going to do is I'm going to compare this cluster membership assignment with the actual glass type, and let's see what happens. Do I have at least one glass type that sits in the same cluster? Oh yeah, take a look at this. Guys, take a look at this. So I have my class 1, right, glass type 1 and glass type 3 perfectly assigned to the first cluster. See this? This method perfectly put all glass samples of class 1 and class 3 in the same cluster. For the class 2, approximately, right? This is approximately perfect for this second class. Now for the class 5, close, right? And then 6 is hard to tell because we only have 9 samples. And the class 7, it's mostly here, right? So if you look at it, these two are just perfect. See this? Okay. And now what I can also do is I can do the cluster plot, right? Oops. Yes, this is my cluster plot here. And I can also do this one. Let's see. Yeah, so here what this did is I just plotted the points, right? I just plotted the points. Now what we can do, I'll show you this first, and then we're going to run this without scaling the data. You'll see the difference. Okay, so now here, this is a little documentation. If you type the question mark, it will show you the help page for the package, right? This shows the help page for the cluster implementation and for this implementation. So if you add this to your assignment, it could add value. I think this could add value to your assignment. Okay, and also make sure to add the elbow method to estimate the optimal k-value. I mean, if I were you, I would. Okay, so now let's do this. Let's reread the data into the class. I'm going to reread this, and now I'm going to do this here. I'm going to scroll down, and I'm going to do this. Run. I'm going to remove ID and remove type, but I'm not going to run this code. I'm not going to scale right now. I'm going to do this. I don't need to set seed again because I already ran it in this session. Okay, so now let's look at this. Okay, so I just did this, and now I'm going to scroll all the way down, and let's see what's gonna happen here. Okay, see this? I have this split slightly differently. Of course, the type 7, it's always good, right? It's in here. Now I have the types 1, right? The class 1, it's split between 2 and 3. My class 2 is kind of like split between cluster 1 and 2. See this? But at least it's not split among the 3 clusters. Well, a little better, but still not. So let's look at this one. What happens with 3? And you will see it that this is actually the best if you don't scale the data. That's gonna be the big difference, right? Do you see the difference? Most of it, see this? We are not, the first type of glass is no longer split among the 3 clusters. And here, right, if you look at the glass type 2, mostly it's in this one, in the second cluster, right? It's a little bit well, but you know, here somewhere you might have one variable that has a higher influence on results than other variable. So just few things to keep in mind. The results are different because if I go in here and if I run this guy right here on non-scale data, let's see what I'm gonna get. I believe it's going to be 3 this time. Yes, it's 3. See this? So basically, not scaling gives me different results. This is what happened now. And I'm gonna take a look at this, but I'm interested to see this. See that? Well, I would say almost same. Well, take a look at this. What we have? We have type 1 and type 3 still falls in the same cluster, right? But this is really, well, how much does it help? Well, take a look at it. Type 7, right, fell in cluster 3. Type 1 and 3 entirely fall in the first one. This one, most of it fall in first, right? Fall in first cluster. Here we just have pieces from here and there, right? So basically, it's two. It's basically two clusters is an optimal k-value. But what you also could do is you could add another input parameter to this here. Right now, this is what I ran, right? But I can also do this. I can specify that I want to look at the values between, perhaps let's look at the values between 4 and 15 and see what it does. Right? And then I'm gonna do this. I'm gonna do, oh, this is here. It's here. What did it do? 4. See this? So 4. Basically, the best value is 3, now it's 4. But what happens if I take this, let's take between 2 and 15, it's probably gonna give me 3. It's gonna give me 3, I think. Yeah, it's gonna give me 3. So 3, 4, and the next one I think it's gonna pick 6. If I eliminate, if I try to do this, right? So sometimes I have a requirement that I must have at least 5 groups but no more than 10. In just my requirement perhaps, right? So I think it's gonna pick 6. 7, okay. For non-scale data it's 7, but if I scale data it's gonna be 6. So scaling makes a difference, but in this case you saw it, right? If I did not scale it, I get 3 clusters, but you saw what happened in the second cluster. It's kind of like in between, right? It had a little bit of everything, but I could not find a class that perfectly fit into the second cluster in the middle. See that? So in this case, the optimal k-value is 2. And also, if you look at the elbow method, that's where the inflection point was, right? If I look at this plot in here, this is where, oops, it's one of the plots. This is where I had my inflection point. It's right here, see? K equals 2. So this is what you're going to do in your homework assignment. Especially, well, I remember in the exercise, you were asked to compare the sum of square distances, and you were asked to run the method for several k-values, right? And then compare the total sum of squared and the sum of squared inside the cluster, right? So this is what you did, but you probably weren't asked to do the elbow method, right? And I think it needs to be added, but for right now, make sure that you understand it, because this could add value to your assignment that you submit. Just remember that, right? So this is what I did here. We ran this method, right? And then we looked at different components, right? And then we also looked at the comparison of clusters to class. Usually you don't have the class label, but in here you have it just for the purpose of the experiment, for the purpose of learning it, right? And also we could go and take a look at what happens, because I did not run for k equals 3, and this is the data was not scaled, right? So now it shows you that you should actually scale the data, right? So I just showed you as an example here. So let's run this and let's see what happens. Right, this is 3. But does it really make sense? See what's happening in the third cluster here? It's kind of like this. It has some of glass type 2, right? Some of it. It has about half of glass type 5, but not most of it. And it has 2 pieces of glass type 6, but it does not have, we cannot find a single class that falls into this here. We cannot find anything that falls exactly into this third cluster, right? So see, do you see the problem here? But if I do the elbow plot for this, elbow plot is going to tell me 3. but it's not the case. See that? It's not the case. It's because I did not scale my data, so that's a problem here, right? Take a look at this. This is what it's gonna do right now. See that? Well, it still shows 2. But remember that the optimal k-value is not 3, it's 2, because what you have to do is, let's do it the right way again. We go into reload this. Oops. I'm going to reload this. And I'm going to reset that here. Because this is the right way to do it. You have to scale your data, right? Because you saw what was happening. Well, you don't have to set again, but I'm doing it again. I'm running it again, right? And then take a look at this. So that was 6, right? And then you're gonna look at this one. Yes, cluster to class analysis. See this? Now I'm gonna look at the 6. This is what happens was I have the first class type, right? Well, it's kind of like split, right? But if you look at the cluster 2, see this? It took 20, which is 1/3, right? It just, I cannot find here a class. Well, actually, class 7, this is perfect, right? Because even if you look at the plot, you see a lot of overlap. But this one, class 7, this is just almost perfect. Everything in the 5th cluster. But you look at the 3. I mean, is it really useful? You take a look at what happened if you do the cluster to class comparison. Well, in real life, you're not going to have the class labels. There are some data sets without the class label, right? And also, well, let's try the 2. Oh, did I do... Oh, wait. This is just plot the first 2 variables. This is just plot 2 variables. I didn't run the method with k equals 2, did I? No, I did not. But if you do that, let's actually try that. Let's try that. So I have to do this. I'm using these arrows to go back. And I'm gonna do the k equals 2. And now I'm going to run this command, right? Okay. Well, there is still a problem, but we're doing better. See this? Most of the class type 1 is in the first cluster, class type 2, class type 3. Well, here you've got mostly 5. Well, not sure what happened, but it's not fully what I wanted to see, but well, it's not fully what I wanted to see. Well, so what you need to do in your homework, you're just playing around. You're just playing around with different k values, and you're going to do the elbow plot, and you're going to look for inflection point, right? This is what you're going to do. And if you want to, you're going to explore this implementation, right? This implementation that I did. Okay? So now I'm going to give you an opportunity to ask questions. Let me look at the chat. Do we have questions? No? I want you guys to ask questions. And important thing, yes, okay, so let's take a look. Okay, question. Sometimes we know that the case should be based on our knowledge. Okay, but our plot indicates a different k value is optimum. Okay, as an example, we are analyzing handwritten digits. Okay, 0 through 9. So k should be 10. Okay, 1 cluster per digit. But wait a minute. Wait a minute. It does not mean that you could put, okay, you could be analyzing handwritten digits, but some digits could be similar. See that? Well, the optimal k value could still be, it could still be 4. That's right, because first of all, are you sure that the numbers are from 0 to 9? I'm a little bit not familiar with a data set. I have not looked at it, but are we always assume that the numbers are in a decimal, 0 through 10? Or could they be like an octal, right? It could be 0 through 7, or it could be the 0, 1, 2, 3, 4, 9, and then it's A for 11, right? A for 10, B for 11, right? So, well, you have to try, because uh, sometimes 9 could be same as 6, right? It could also depends on how you write it, because number 7 could look similar to number 1. Especially depends on the culture, depends on how you write 7. Some people write it with a line in the middle, some people don't put a line in the middle. And then depends on how you write letter 9. I write it based on my handwriting, it looks like a letter G, because sometimes when I write something on a board, perhaps if it's a face-to-face meeting, people keep asking me why is it a G, but that's how I write 9, right? Also, number 1, people write it slightly different, right? Number 7, if you omit the line, it could look close to number 4, it could look close to a 1. So sometimes the numbers are written in that way that we cannot clearly understand what it is, right? Is it number 9 or is it letter G? So basically, we have to have a big picture, so to speak, right? Sometimes we don't know. Sometimes number 4 could look as like number 1 if the line in the middle got erased. Or if we flip number 9, look at it, 6 and 9, right? If you flip it, they could look the same. So, because it also depends how you read it. Well, I'm just trying to think outside the box here. Okay? Well, I hope it helps. Yeah. I mean, that's a matter of interpretation, because we don't see it. And later, if you look at the later what you will do when you get to big data class, you could do, perhaps, if you look at it, you could use clustering method to identify similar pictures. Perhaps you have, well, you don't know what's in the picture, but based on some kind of like pre-programmed, right, object identification, you could group similar images in the same group. You're going to do that to identify the terms. The text mining identifies the terms that may appear in the same document. You're going to identify the documents based on similarity, so that's application to clustering. You will see that again. You will use this method in the data 650. Because I'm a TA this semester. I officially TA data 650, and I've been doing it since the course was taught for the first time. I've been a very long time in this program. So, yeah. But this is a real-life example of clustering. You want to group things together, like images, right? Perhaps usually when you sort your pictures, you manually look at each picture, and you can sort it by occasion. You can sort it by perhaps a special, like occasion, special event, or it could be something like pictures of your pet, right? Or it could be something else, right? Something on your field trip, different place you visit. Well, it's just an example, right? So clustering would be a good method, because you don't have the predefined number of categories, right? And you try to estimate how to group the images, perhaps, right? So this is upcoming. I just try to motivate you what is coming in the future, right? So, and yeah, you can actually do clustering for your text mining, for your group assignment, right? If you look at some examples, there is a k-means clustering, okay? And there is also the hierarchical clustering, dendrograms. One thing to keep in mind about these plots, they might not work well for the very large data sets. So just keep that in mind. It might not look nice for the large data set. the cluster plot that I showed you, when you plot all of the points. Okay, just keep that in mind. So if you were doing it with text, you would probably have to eliminate the stop words, the words that are frequent but they don't really add values, such as the, and then the articles, right? You want to eliminate the frequent terms that don't add value before you do that. So just something to keep in mind, right? Yeah. Well, oh yeah, I just remembered the handwritten digits. I think I may have put the dataset in there. So would you please send us the video, the presentation? Oh yes. Okay, so this is, yes. I understand the assignment is due Sunday. This is what's gonna happen. I will receive the link to the recording, right? And I'll receive the link to the recording. Then I'm going to upload it to YouTube, and after that I'm going to send this file to the professors. And it depends on when the professors give it to you, but I will send everything to professors tonight. So I will ask them, if it's possible to share it with you. Yes, because remember your assignment is due on Sunday, right? Sunday midnight Eastern time. Okay, I'll do what I can. Yeah. Yeah. And the thing is, you already had exercise, right? And this is assignment. It was a big chunk of a point. Uh, why does the curve? Okay, the question is, why does the curve? Okay, why does it drop? Oh, okay. Okay, why does it drop? Well, it's because the sum of squared distances inside the cluster, well, it's supposed to drop. Because what are you doing actually? You're taking this. Do you remember this here? The more points you have, see this here are my cluster center, and I have several cluster centers, and this is a point assigned to this cluster. I take this distance here, right? I have this distance here. When I have more clusters, the distances are going to be smaller. It's because, see this? This is the center A. If I put another center closer to the center B, my B is going to go to another center, right? To the closest center. The distances are going to be smaller. The higher the K, the distances are going to be smaller. Well, sometimes it could go a little up and down. Of course, it could go a little bit up and down, yes. But eventually it drops. But there is also a limit to how far it's going to drop, see? So at some point we just have to say, okay, well, that's good enough. Because another problem is that you don't want the K to be equal to the number of instances. And we are not solving the problem if we put each glass sample in on a separate shelf, right? So yeah, it's just like this. It's not a little smooth, but it's like up and down. But you want to look at the inflection point. I hope I answered the question, Brian. Yes, I hope yes. Excellent. Yes. But I really love the questions, because when I don't get any questions, I start asking questions, right? So you need to make sure that you understand the difference between supervised and unsupervised learning, right? This is important. So we are not assigning the weight to variables. We are not, we don't have a label here. We just did it for experiment. But in general, you're not going to have a label. You're going to have the chemical compound information, and your task is to identify the similar glass samples. Well, here it's samples. In the exercise example, you have the seeds, right? Then there is also an example on the wine data. Yeah. But this is a glass data. This data set, you'll find it useful for classification and for the clustering. Yes, you'll see it in the classification problems a lot. Alright? So let's see if we have more questions. I love questions. And I'll see what I can do to make sure that you have this file. Okay? So let's see if you have more questions. This is excellent opportunity to ask questions. Okay? So we are very close to the semester end, and I need to congratulate you guys to getting this far, right? So you're gonna be 3 down, 3 to go in your program, right? This is the third main class, you have 3 left. Yeah. 3 down, 3 to go, halfway there. Alright? So more questions? Questions? This is a perfect opportunity. Well, if there are no more questions, then I'm going to stop the sharing the screen, and I'm going to stop the recording, and I guess I would like to thank everybody who was able to attend, and thank to everybody who will be able to watch this presentation. I'm going to end the recording, and everybody have a great night. Thank you.